Good evening and welcome to Evolutionary Software Architects with Neil Ford. My name's Henrietta and I work on the community team here at eSynergy Solutions. eSynergy specialise in open source and cloud resourcing. If you're looking for a new opportunity, we can help you find the right role tailored to your skills and experience on either a contract or permanent basis. So please send over your updated CV. Should you be looking to build out your team, we can help you with hiring and attracting top talent. Alongside this, we can also help you with upskilling your employees around the latest open source and cloud technologies. Now, moving on to some housekeeping. If you have any questions for Neil, please fire them over via the question box throughout, and Neil will answer them at the end of his talk. We are recording this session and all the slides and recordings will be made available and sent to you tomorrow by email along with my contact details. Now I'm going to pass you over to Neil to begin the talk.
Thanks so much. Can everyone see the screen and hear me okay? If not, just let her know via the chat. I'm talking today about evolutionary architecture as it applies to software. And this is based on a book that I'm currently working on with two other authors, Rebecca Parsons and Pat Qua, who's based in the UK. And what we're trying to do is look at architecture through a slightly different lens. Some of the things I'm going to talk about you've heard before, but probably not in the same context that I'm going to be talking about them. And part of this is observations about software architecture born out of many years of watching software architectures and how they change over time. And one of the interesting characteristics of software architecture is this idea that it exists in a dynamic equilibrium. Because when you look at the software architecture ecosystem, it's a stable, well-balanced equilibrium, and then something unexpected shows up, and it shifts everything. This is a concept from physics and biology, where if you have molecules and you open a room, they will disperse and evenly fill the entire room. The same with molecular diffusion, as you can see from this animation here. And so the way this applies to software architecture is, let's say that you get together with your other enterprise architect friends and you make a 5-year plan for architecture, and then all of a sudden Docker shows up 2 years in. Your plan for architecture is completely shot because now the entire ecosystem has changed. This is the dynamic equilibrium we're talking about. Software development world always exists in this dynamic equilibrium, and for a long time we tried to figure out how to predict the future as a way of solving this problem, but we've now realized that that's a terrible way to solve this problem. Instead, what we need to do is get better at building architectures who can accommodate this inevitable dynamic equilibrium that exists in the software development ecosystem. And so let me give you our definition of evolutionary architecture, and then I'll talk about a bunch of the nuances of this definition. So this is our working definition, and this is still very much a work in progress as we're working on this evolutionary architecture book. But our working definition is an evolutionary architecture supports continual and incremental change as a first principle among multiple dimensions. Let me explain what I mean by this definition. First of all, let's talk about several different types of architecture. Software architecture is really a matter of perspective when you look at a software project, because you can talk about the technical architecture of the project. This is what we normally think about when you think about software architecture, is the technical architecture. This is how the web frameworks and the database libraries and the connections to mainframes, those are all parts of the technical architecture of how the technical pieces fit together. There's also frequently a data architecture. This is database schemas and table layouts and those kinds of activities. You also have a security architecture, which defines security policies and how those things are going to be defined. So each of these is a perspective on architecture. And over the last few years, we've gained a new perspective on architecture, which is this domain perspective on architecture. which is one that was largely ignored for a long time, but largely came about because of the practices in domain-driven design, which is a very popular book by Eric Evans. It's ostensibly an object modeling technique, and a really terrific implementation guide for domain-driven design is the Von Vernon book, Implementing Domain-Driven Design. This has been really influential on a lot of architects because what domain-driven design has done is introduced a new perspective on architecture. One of the things that are clearly delineated, but no one outside that bounded context knows what all of those details are. You can ask that domain questions about itself and get answers, but you don't know any intimate details like database schemas or class hierarchies or any other implementation details. What has happened in the architecture world is they've taken this logical concept of bounded context and married it with the engineering practices in continuous delivery. And what that has given us is a brand new perspective on architecture, this domain perspective on architecture. And so let's talk for a second about the evolvability of architectures, and this will get to this definition of architectural dimensions that I referred to earlier. And let's first look at the degenerate case, which is no architecture whatsoever, which is the ever so charming and quite common big ball of mud architecture. This is an actual diagram from a client project that I was on. This is the afferent and efferent coupling between the classes. So the teeny tiny little dots on the outer perimeter are classes, and the red lines are connections between them. And the strength of the connection is indicated by the boldness of the line. This architecture cannot be evolved at all. This has 0 dimensions of evolvability. And of course, this is one of the reasons you don't like this architectural pattern, is because it's very hard to make changes here, because everything is highly coupled to everything else. A single change in one place ripples across and has huge impacts on unrelated parts of the system. But let's look at a more organized architecture, the really common one, the layered architecture pattern. This particular example of layered architecture has presentation, business, persistence, and database layers. And of course, the reason you build, or one of the reasons you build a layered architecture, is to allow you to make changes at each of these layers. So for example, if I want to change out the persistence mechanism I'm using in my application, I should, in theory, be able to change out just the persistence layer and have little effect on the database or business layer and no effect on the presentation layer, because I've built some level of evolvability into my architecture. And so the dimensions of evolvability for this particular technical architecture is 1, because I can evolve along the technical architecture dimension. Now you'll notice there are actually 4 layers here, so I have 4 different opportunities for evolution, but really only along one dimension, which is the technical architecture dimension, because that's how I've organized this architecture. Now, one of the characteristics of the layered architecture is that you want these layers to be closed. And what a closed layer means is that each request has to go through each one of the layers before it, each request has to go through each layer, can't skip any of the layers, in other words. But one of the common patterns that people implement is to open these layers because of an anti-pattern that's known as the architecture sinkhole anti-pattern. So let's say that you have a services layer here, and that services layer is optional for some requests. Some requests really need some processing in that services layer, but some don't. And so the architecture sinkhole anti-pattern is when you have a layer where that layer does nothing but transform the input from the layer above and just pass it to the layer below. That's the architecture sinkhole anti-pattern. And so one of the ways that you avoid the architecture sinkhole is to open one of the layers, making it optional. So in this scenario, you can call straight from the business layer to the persistence layer, or you can go through the services layer if it is actually adding some value to what you're doing. So this is a very common solution to this architecture sinkhole anti-pattern. And so here, the opportunities for evolution have gone down because we've now coupled more layers together than we normally would in an architecture. The dimensions of evolvability are still one. We still evolve along a technical architecture, but the opportunities for evolution really come down to how much extra coupling we allow that violates the general principle of this architecture. Let's look at the evolutionary characteristics of another really common architectural pattern, which is the microkernel architecture. This is commonly found in things like browsers and in build tools, anything really that has a plug-in API. This allows you to evolve this architecture by building plugins in a well-defined way, and you can evolve its behavior over time. But again, we only have one dimension of evolvability here, which is accessed through that plugin API. Now, all the ones that I've been talking about so far are physical, technical architectures, but there are also conceptual architectures that you can consider the evolvability of as well. Consider REST plus Hadios, the level 3 of REST. And in this world, when you make a request to a service, you get a response back, and part of that response includes links for the further steps within that workflow. And so you may get 3 different links back as part of the return from a request. You then follow one of those links, which then gets you results back that has other links in it. You follow one of those. And so what you're allowing in this architecture is the server side to define the steps and the details of the workflow. But again, we really just have one dimension of evolvability here, which is along what I'm calling the workflow dimension. You can change the steps in a workflow, and this is in fact embedded inside some other technical architecture, and so this in many ways forms a conceptual architecture that sits on top of a technical architecture. But let's talk for a second about this domain shift that I referenced a little bit earlier. A few years ago, we started realizing, because of several factors, which I will touch on in a moment, that we're missing the domain perspective of architecture in many cases. So if you look at the traditional layered architecture, where does customer live in the layered architecture? Well, part of customer lives in the presentation layer, and part lives in the business layer, and so it's kind of spread out across the architecture. And so from a domain perspective on the architecture, we have 0 dimensions of evolvability. In other words, it's really hard for us to go into this architecture and make a change to just customer, because it's going to affect multiple layers, because customer is sort of smeared out across our technical architecture. Which brings us to everyone's favorite poster child architecture right now, which is microservices. And this one is quite interesting from our standpoint, because in the microservices world, one of the defining characteristics of microservice architectures is that each service forms its own bounded context. In other words, it is operationally distinct from all the other services that run in this ecosystem. Which means that you can easily take one of these services out and put another one in its place, and because there's 0 coupling to these other services, there's no ripple impact from that change. And so the dimensions of evolvability here are really N, where N is the number of services. Because you've encapsulated the technical architecture entirely inside each one of these services, the coupling doesn't prevent you from evolving in any way that you want to. And this is a good example of an evolutionary architecture, because now we can easily take that single bounded context and replace it with another one that meets the same kind of contract without affecting the operationability of any of these other running components. This is a great example of an evolutionary architecture, because this one supports evolution along more than one dimension. And so let's go back to the definition I gave you before. An evolutionary architecture supports continual and incremental change as a first principle along multiple dimensions. And so it can be argued that the purpose of software architecture in general is to allow evolution. What we're interested in are architectures that allow evolution along multiple dimensions, because it gives you some interesting kinds of capabilities. So that's the multiple dimensions part of the definition. Let's talk about incremental change. And this really comes from and is inspired by the engineering practices in the continuous delivery world. So let's say that you live in an ecosystem that has very mature engineering practices, and in this world, components are deployed into production, meaning that we deploy components by physically moving those components into production, but that doesn't necessarily mean that the features are released, because we commonly use techniques like feature toggles, which I'll touch on again in just a moment, to toggle features on and off. By separating the deployment from releasing features, that allows us to investigate all the operational aspects of this component before we allow users to start interacting with it. This also allows us to deploy components side by side that may have very similar feature sets. And in this world, we haven't really impacted our users yet, because very often applications consist of the routing between these components that we've deployed. And so let's talk about this from an incremental change standpoint. And this is one of the benefits of having an evolutionary architecture. So let's say that you run a widget catalog site. And one of the services that you provide is star ratings, so that people can come in and give your catalog items a rating of how much they enjoy your catalog items. Then at some point, one of your team implements a better star rating service that allows half-star ratings, so you can rate something 4.5 stars rather than just whole number stars. And we can deploy this into the ecosystem without disrupting anything, because it's just another service running in the ecosystem. And each of these other places that need star ratings, like the catalog page or maybe the sales or promotion page, on their own schedule, they can start implementing half-star ratings rather than singular ratings, and over time, people will evolve over to this new improved capability. In architectures like this, we monitor not only the services, but also the routes between services. And any service that's no longer being routed to is automatically disintegrated out of the ecosystem. This is what we mean by incremental change. We want to support continual and incremental change as a first principle along multiple dimensions of the architecture. This is our working definition, and we're quite curious to investigate the characteristics and the principles behind this family of architectures. Brings me to the agenda for the rest of this talk, which I have about 15 or 20 minutes. And I'm going to touch on each of these things very briefly. So let's talk some about some of the principles behind and characteristics of these kinds of systems. One quite common characteristic in an evolutionary architecture is decentralized data management. Rather than using a single monolithic database along with a monolithic architecture, very often, just as in the microservices world, you have a single database per service, or at least a single context, data context per service. This gets directly to the Sam Newman's advice, who wrote the terrific Building Microservices book for O'Reilly. Avoid distributed transactions if at all possible. And so one of the things that evolutionary architectures encourage you to do is limit the scope of transactions as much as possible. People get kind of sloppy with transactions when it's a very easy thing to do, but very often it makes changing things very difficult, because that transactional context is temporal coupling between otherwise unrelated parts of your system, and so that can cause ripple effects when you try to change things. Another side effect of this kind of architecture is decentralized governance, particularly in a world like microservices, where you've encapsulated the technical architecture inside each service. Let's say that one of your service teams decides that they want to implement something like Mongo, and they just realize a few weeks later that that was a terrible idea, and they decide to switch to Postgres instead. Nobody else in this architecture cares, because no one is coupled to that database. In fact, the other services don't even know that if this service has a relational database. It may be some other kind of store. This frees up governance and actually makes governance much more simple in this world. And this is one of the really tricky things when you talk about architectural governance, particularly in monoliths, because when you make decisions about technical architecture in monoliths, you very often are making decisions for everybody, because they all share that same framework, that same library. Very often you have to accommodate the 20% most complex part of your architecture, which means that you punish the 80% of people who have much simpler needs but are forced to use the most complicated thing because you're having to accommodate the most complicated problem that you run into. In the microservices world, or in evolutionary architecture, we encourage polyglot solutions in trying to right-size a technology choice for the problem we're trying to solve. Now, we're not trying to say that this is the Wild West and that every team gets to pick their own artisanal development stack. But what we are trying to say here is that why over-specify when you don't have to? Try to pick the right technology stack for the size problem you're trying to solve. And this actually makes enterprise architecture governance much easier. What you tend to do from an enterprise governance standpoint is pick several suitable stacks for very small problems, medium-sized problems, and huge scale problems, and implement your services that way. A lot of these characteristics, finally, when you get to talking about architecture, come down to coupling and how coupled things are to one another. And in fact, we do a lot of discussion in the book about coupling and cohesion and how that contrasts with composition. So those are a bunch of characteristics of these architectures. Let's talk about some principles of these architectures. And I'm going to start this section with the poetry of Donald Rumsfeld. And actually, I'm not. Sorry, this is my architecture principles. This is the poetry of Donald Rumsfeld. Donald Rumsfeld very famously at one point said, there are known unknowns. That is to say, there are things we now know we don't know, but there are also unknown unknowns. There are things we do not know we don't know. And he didn't realize it at the time, but he was really talking about software and particularly architecture when he said that, because this is the thing that really kills big design up front and planning in software. It's the unknown unknowns. You can think about the known unknowns. For example, we're going to do geocoding in the next project, and I don't know anything about geocoding, but I know that it exists. But it's the unknown unknowns that end up nabbing you. So many people a few years ago made these really beautiful plans about things, and then Docker became the unknown unknown that completely disrupted all of their plans because it disrupted the dynamic equilibrium that the software world exists within. And so one of our principles in this world is we try to prefer pro and reactive to predictive. Rather than try to predict how things are going to happen, can we be reactive and smart about building things so that we can react to them more gracefully? And let me give you a concrete example of this. This is from a project that I was on for a while. This is a Ruby on Rails project, and it's the evolution of how asynchronous messaging ended up working in this project. So this is a project that needed large uploads of photos in batches, and so a very early request for this project was to have asynchronous uploads so that you get a progress bar or you can start a job and come back to it later. And so we looked at, of course, the traditional way you implement something like this in software is with a message queue. And we thought about doing a message queue for this, but this is a very simple problem. We did a couple of spikes, and we discovered this little thing called background RB that solved the problem. It was good enough. Now, when we implemented it, we put it behind the Ruby equivalent of an interface because we figured that we would eventually need to change this, but it was good enough for now. At about the year mark in this project, a second request for asynchronicity came in, which are timed events, for regularly scheduled events to kick things off. We again investigated maybe adding a proper message queue, but just spin up a new instance of background RB and it worked fine. Then at about the 2-year mark of this project, a third request for asynchronicity came in, which are continuously run things like updating caches and counts, things like that. And at that point, we decided it was time to move to a real message queue, and so we implemented Starling, which is a message queue in the Ruby on Rails world. And when that time came, it took one pair of developers less than a week to swap out background RB for this new message queue. And so what we did here, rather than trying to predict the future and just buying the most expensive, most full-featured message queue we can as soon as that requirement comes in, we delayed that decision by putting it behind an interface and tried to be both proactive in looking at it as to determine when its usefulness had expired for the solution that we had, and reactive to look at that and make it so that we can make that change when that occurs. That's what we mean by being proactive versus reactive. Proactive, reactive versus predictive. Another one of these principles is this idea of bringing the pain forward. Back in the earlier days of software development in the 70s and 80s and into the early 90s, a really common workflow for doing software development was to have all people work in isolation from one another, and then when they got to the end of the project, there was a giant integration phase where they all took their work and tried to integrate it all together and get it to all make one cohesive build. This is a really common practice in those days. Back in the early 90s, a group of developers got together who had collectively worked on lots and lots of projects, and they were kind of depressed at the state of the software development world because it didn't seem like any process that people were using was particularly effective. And so what they decided was, we're just going to take the things that from our collective experience we know work really well and push those things as far to the extreme as possible. This, of course, is the extreme programming guys. And one of the things they attacked was this common integration phase problem from before. And of course, what they did was invent this idea of continuous integration. And as soon as you make changes, integrate that with all those other changes. And the mantra behind that invention was this idea of bring the pain forward. And this is a really important principle that shows up in lots and lots of contexts in the software development world. Because if you look at the amount of pain that you pay over time, and by pain here I mean engineering headaches, things that are expensive to do manually, things that you have to do all the time, just little friction, engineering friction that pops up. You would think that over time pain would get linearly worse as your project, the source code base gets larger, as you get more and more integration points, etc. But there are lots of problems in software that, for interesting reasons, doesn't go up linearly, it goes up exponentially. And I think integration is one of those things. And this is exactly what the bring the pain forward mantra was about from the XP guys, is if you can attack problems in the really early parts of this curve, you pay a lot less engineering pain for it than you do later on. And this example, this principle shows up in lots of places within continuous delivery in the microservices world. This is really the motivation for things like deployment pipelines in the continuous delivery world, to try to get things as integrated with each other as eagerly as possible, to have automated processes to go in and do that. That's really critical for an evolutionary architecture because you want to be able to put changes live alongside the existing functionality as aggressively as possible. We also see this in database migrations and refactoring. One of the huge hindrances in having an evolutionary architecture is having a really fossilized database schema that you've never refactored and don't have a good way to make incremental change to. And automation, of course, we are huge fans of automation. A lot of continuous delivery is about making automation better and smarter. So those are all things about process. Let's talk for a bit about people and about Conway's law. Last March, O'Reilly had the their first software architecture conference in Boston. It's coming back in April in New York this year, and in London in October. And I was on the program committee for that conference. And more than half the abstracts were about microservices of one kind or another. We didn't do that many talks about that, but we had many, many talks about microservices. And within the conference, Conway's law became a drinking game because every talk ended up mentioning Conway's law at some point or another. This was an observation that Melvin Conway made back in 1968, that organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. What that suggests for software projects is that if you have a bunch of specialists that are striated into layers, UI specialists, middleware specialists, and DBAs, you will probably end up with those layers in your architecture. And back 15 years ago, there were compelling reasons to do this because at that time, the dynamic equilibrium of the software world said that infrastructure is expensive, and so you want to be able to partition that away from everything else, But then the world changed with tools like Puppet and Chef and containerization like Docker, and open source software has had a huge impact because now you don't have to worry about licensing for operating systems, which means you're not compelled to try to run as many things as possible on middleware anymore the way it used to be. So what we're seeing is a lot of people shifting their perspective. Because like I say, in the monolithic world, it made sense to organize your teams in layers that resemble your monolith. But now we're thinking that a better way to do this is to organize people around domains, particularly if you're building a domain-centric architecture. Conway's law suggests that you're going to be pitching against windmills if you try to have a siloed workforce building domain-centric services. Why not build the teams that look like the architecture you want, and it's easier to achieve that architecture. We have two names for this. One is the inverse Conway maneuver. It's really the realization that Conway's law is going to happen whether you want it to or not. And so why not leverage that rather than avoid it? If you really want to impress someone about this, you can refer to this as domain architecture isomorphism. This is how the domain and the architecture map to one another, but that phrase is probably best left for discussions with enterprise architects about this. Really what the inverse Conway maneuver says is that you build cross-functional teams that look like the capabilities that you're building and leverage Conway's law. So let's talk a second about fitness functions, which we haven't touched on much yet. We're still doing a lot of research on this, but this is a common way to handle directing the evolution of architecture. So we're talking about evolutionary architecture here, which is partially about the behavior of architectural elements, but we're also trying to pull in the behavior of evolutionary biology as well, because in evolutionary biology, of course, evolution works to incrementally improve things over time. We want to do the same thing in software, and in fact, it's just too expensive to create a software system that lets you randomly try things until it gets better. And so that's what a fitness function is. This is a function that we can apply to an architectural element to say, is it evolving in the way that we want it to evolve or not? And these normally come down in the software world to one of two things, either metrics, or some combination of metrics that tell us something about code bases, or some sort of test. So for example, perhaps one of our fitness functions has to do with a service level agreement about response time. Every page has to show within 3/4 of a second. And so you can build that fitness function in as a test very early on in the architecture and just run this against every time you do make a change to the architecture so that you trip this test anytime you start failing that fitness function. One thing about fitness functions is that you're never going to start the project knowing exactly what those are going to be, and so both these will shift and morph over time and become more and more part of your architecture as you learn more and more about the true nature and characteristics of the architecture you're building. And finally, a few anti-principles, things that make evolutionary architectures really difficult to build. Heavily transactional systems don't work well here. Transactions are a form of temporal coupling, which is just as bad as class or package level coupling. It's just as hard or harder to untangle. So if you have a heavily transactional system, you may not want to pursue this kind of architecture. Certainly any case that you have really highly exuberant coupling is going to be very difficult to build an evolutionary architecture from that. Coding via configuration for things like middleware, enterprise service buses, or business rules engines, all of those things are highly coupled to the infrastructure that they're part of, and it's very hard to make them part of a bounded context. And so it's hard to encapsulate the technical architecture and the deployment characteristics of tools like that. And really strict governance also makes this quite difficult. Normally, really strict governance is motivated by cost savings, not about building really effective architectures. And so those are some of the principles For the practices, I've already touched on this and won't talk much more about this in this particular talk. All the engineering practices of continuous delivery are the things that enable you to make these architectures work. And one of the really common practices that we talk about in continuous delivery are feature toggles. And I'll touch on that here because this really gets to the heart of why you want an architecture like this. So feature toggle is an alternative to doing something like feature branching if you want to implement a cherry picking of new features. A feature toggle is some code that you add to your application. This can be done in frameworks like, for example, ToggleZ in the Java world. There are a variety of different feature flag or feature toggle frameworks. And basically what you do is add that toggle to all the parts of your architecture so that you can flip a toggle and turn a particular feature on or off as you want to. Having that capability really becomes an experimentation enabler. In fact, many of these continuous delivery practices enable you to do that, along with things like spikes, which is really common in the Agile world, time box, experimental coding exercises, having a trusted user that you can play experiments on, and a combination of both metrics and fitness functions that let you know if your architecture is getting better or not. Which brings us to one of the really great advantages of having something like an evolutionary architecture, because it can change the way that you think about and build systems. This really brings us to this idea of hypothesis-driven development. Rather than going into a room and brainstorming and coming up with a giant backlog of things that we want our project to do, instead, if we have a really good evolutionary architecture system, we can get together and think about what is our strategy and business goals, and rather than come up with a bunch of features we're going to implement which people may or may not like, we're going to generate a bunch of ideas and build a portfolio of those ideas that we can run as experiments. This idea of hypothesis-driven development. We select hypotheses, and let's say that we select several experiments to run for our users. We have feature toggles, so we can do A/B testing to see which thing they like better. And maybe one of these experiments we start running it and then we realize that it's not quite what we want, but we see what would make it better and we pivot and continue along that path. Maybe another experiment is just disastrous and so we fold that experiment. Maybe one of them the community really engages with and we can double down on that one and put a lot more time and effort into building that. Of course, each of these are accompanied by feedback loops, but having an evolutionary architecture where you can put multiple things into your architecture at one time, do A/B testing against them, allows you to interact with the people in your ecosystem a whole lot better. We believe that evolutionary architecture is going to become inevitable in the software world because of the dynamic equilibrium problem, because it's never going to go away. So it doesn't matter what technology it is, insert some new technology here, it's going to always upset this dynamic equilibrium. And so that's why we are so interested in studying these family of architectures that allow you to accommodate the dynamic equilibrium nature of the software development ecosystem. So stay tuned. We're in the early days of working on this book, but both myself and Rebecca and Pat are starting to talk about all these things as we're building them, and so this is a first example of that. That's all I have from a content perspective, and I have a little bit of time left over if anyone wants to ask me questions. I've got a few questions already. You can ask questions in the chat window. One of the questions I have is, does legacy code cause an issue in evolutionary architecture? It does, because very frequently legacy code was never designed to be evolved in any particular way. So maybe your legacy application has a layered architecture and you can still evolve along each layer, but it's very difficult to evolve past those layers in a multi-dimensional way. And that's really the essence of what we're getting at when we talk about an evolutionary architecture. Legacy code can be made more evolutionary if you can encapsulate it. So that's what a lot of people are doing with Docker and containerization, is finding a way to encapsulate some of that legacy code so that they can start treating it as its own bounded context. Do other people have questions about this? I have a question here about is microservices the only one of these kind of architectures? It's not. It really comes down to intent. So what we're looking at when we're looking at is an architecture evolutionary or not, it really ultimately boils down to what are the coupling characteristics of that architecture. And the coupling characteristics that are going to impede you making changes to it. So for example, if you have a big ball of mud architecture, like the one I showed you before, that's really hard to evolve any of the behavior of that system because everything is coupled to everything else. But maybe you have a really well-defined and really well-adhered to layered architecture, but you have really tangled transactions, a heavily transactional system. You're going to have as much trouble of changing that as you are in something that's really highly technically coupled at the class level because you have a temporal coupling at the transaction level. So it really depends on what your perspective, your architecture is as to which dimension can you evolve by and how difficult is it going to be to retrofit your architecture to evolve along that dimension. The question is, what are the fundamental people skills needed for evolutionary architecture to be successful? Is there a particular skill set? Clearly, this is true in just about all of architecture now, that you need to get better at kind of architecture soft skills and convince people that they need to do this. Because if you're really going to invest heavily in something like an evolutionary architecture, that's probably going to entail changes in places like your operations group or your QA group or your DBAs. And so convincing them this is a good thing is tricky. My best advice here is a demonstration trumps discussion. Don't try to explain how it's going to make it better for them. Illustrate by showing them how it's going to make them better, and you'll get a lot longer toward convincing them. Another question I have here is, how do we apply this to greenfield projects? The easiest way to apply this to a greenfield project now is to build a microservice architecture and be very careful to encapsulate each one of the services completely from all the other services. That makes it really highly evolutionary and will make it super easy to make changes over time. That's actually the best case scenario. Many people are in the scenario where they have a monolith and are slowly decomposing it into more of a services or microservices kind of architecture. Another question is, what is my feel for the percentage of uptake for evolutionary architecture at the moment? It's pretty low at the moment, but the people who are doing this have a gigantic advantage over the people who don't. This is basically an architecture superpower, this ability to make small, incremental, non-breaking changes all the time. Companies who do this are definitely going to have an advantage in fast-moving markets over companies who are not doing this. This is one of the reasons why Netflix has used their technical capabilities so intelligently. They built on top of one of these architectures, and so they can make small incremental changes in almost any direction, which makes it really, really hard to compete with them. And I think that we've only slowly come to realize the inevitability of the dynamic equilibrium in the software world. And so I think we're gonna be forced to get better at this because it's simply too expensive to keep guessing wrong every time we make plans about things and then have to scramble and have to retrofit them and fix them once we've guessed wrong and have to go back and fix them. If we can get better at not doing that, then we're going to end up saving time and effort and sanity. And with that, I think we have just about reached the end of our time. So thanks everyone very much for coming. These slides will be available on my website, neil4.com, if you would like to download a copy of them. They're going to make a copy of this recording of the screencast available as well, so you can contact those folks. And thanks very much for coming. I hope you enjoyed it.